Last week, in this course, Friday last lecture, it will be an interesting day. Maybe some of you going to The Hague. I don't know. Yeah. If you didn't hear about that, ask your fellow students. They'll explain. In the back there, can you view the slides well enough? Noted are good, thanks. I'll continue today the lecture on clustering, and now today embark on explaining some phylogenetic methods to you. Okay, I started doing this. I showed you how clustering might work with these pictures, where clouds of points were encircled. But here's the basic algorithm, and it's a few really simple steps. And this time I stick to saying it's simple. So basically, you work when you cluster on a distance matrix, a dissimilarity matrix. It might be a similarity matrix. Then you would have to convert them into distances. Various formulae to do this, to convert similarity values to distances and the other way around. But basically, how do you start? The first step in any cluster procedure will be, if it's an agglomerative clustering procedure, meaning you take points together from all those points until finally you arrive at one cluster where all the points are contained in. You start always taking as the first cluster, the nearest to 2 points according to the distance criterion you're using. So that's 2 here. Take 2 points at the smallest distance. You all the time do this, also later on. And then, if you have done this, so these say in the similarity matrix, this point and that point will be joined. What will you do is the next algorithmic step. You will calculate what that cluster will be, and you represent that cluster by a single point. Yeah? So that means your matrix is shrinking by 1 dimension each time. So if you do this a number of times, you will find that your matrix will end up having dimensionality 1, and then you have your single cluster as the end product of your activity. And after having done step 3, you just go back to 2. So it's a really simple iterative procedure. So let's do it then. I did this at the end of last lecture, but I'll do it again for you so it becomes clear. So here we have the distance matrix. We start with 4 loose points. They're coined A, B, C, and D. First step B was take the nearest 2 points as the first cluster. So that's just looking in your matrix what the smallest distance is in this case. I hope you agree with me. In this matrix that is 4. So that means the points connected by a distance of 4 will be taken together. And in this case that will be point B and point D. You see that the distance matrix is, I already mentioned that the last time, it's symmetrical. But also in this case you do not need the main diagonal because a distance from a point to itself is not really interesting when you're clustering. Okay? So we ignore all of that, and that is made gray. Okay, so 4, we've done it, and here you see what happens here in the algorithm. Now we have to merge these 2 column rows, and why does it look so funny? Of course, in the real matrix it will be 2 complete rows and also 2 complete columns. But this is how it works if you chop off half the matrix. So we now need to make 1 new row column containing the 2 points B and D, because here they were merged. Yeah? And what is interesting now? Well, according to your distance principle, now you need to recalculate the distances of the remaining points to this new cluster. And this here is under the assumption of single linkage. What was that again? You remember probably. The distance from a point to a cluster was the smallest distance from that point to the nearest point in the cluster. And if you have 2 clusters, you do the same thing. Yeah? Just the nearest possible, the nearest 2 nodes from either cluster represent the distance between the clusters. So why then, and I started asking you, how do you then calculate that the distance from remaining point A to cluster BD is 5? You check the 2 distances that you can make. From A to the cluster, it could either be A to B or A connecting to D, and you look at those distances in the original matrix. And what do you see? AB has a distance of 5, AD has a distance of 9. So under single linkage, where you take the smallest distance, you'll decide to take 5 to the expense of 9, okay? So 5. And the same thing happens if you want the value from C to the cluster. So what distances do you need to check? C to B and C to D, do it, and hopefully you'll find that that is the smallest one is 7. Yeah? Okay, so then you've done this, and then you go back to step 2. What was that again? Take the nearest 2 points, whether they're clusters or points, it doesn't matter. And what do you say? C, the smallest distance is 5. So what will we do? We'll join A to that pre-existing cluster B. Yeah? So you get a cluster ABD here, and now you know it's done. We're back to 1 dimension, but it's always good to calculate the distance. So what do we need to do to come to the 6? You check CA, C to B, C to D, do it, and you'll find that 6 is the smallest one. Yeah? And that means that, you know, the report of this procedure is this dendrogram here. First merger was B and D at a distance of 4. The second was adding A to that cluster at a distance of 5. And the last step is adding C to that cluster at a distance of 6. Okay? Yeah, clear? Important that this is true. Good. We do the same thing again, same data set, but now we do the other distance. Complete linkage, meaning we define the distance between a point and the cluster or between 2 clusters as the largest possible distance you can find. Okay? So what's happening? This is all the same thing. Step 2 was take the nearest point, put all loose points at this point. So there is no difference when you have loose points, you know, it's just the distance. You don't need to worry at this stage about single or complete links, same thing. So what is the smallest distance 4 again? So in our dendrogram you start, as before, putting B and D together at a distance of 4. But now we have to recalculate again the distances from the remaining points being A and C to cluster BD. But what do we see now? Why is that now 9? Anybody? Clear? The 9 is clear. You don't need to speak up. It's only Monday. Yeah, okay. Okay. Good. And then the other one, so A is clear now. That's very good. And C, that it's now 6. That it's now 8, C to BD. You have always, you know, that's very important here as well. Huh? Look in the proper row or column. Yeah, that's a good idea. So, why is that now 8, C2? Again, check CB, check CD, and take the largest in this case. Okay? That's the difference with before. But again, step 2. So, a lot of bachelor students at least, I don't know about the masters, some of you do that as well. They think, we're very clever people. You are, of course. But still, clever people can make mistakes. It might surprise you, but it's true. I see this all the time. So when you think, it was about maximum, you know, complete linkage was about the maximum distance that defines the distance between points and clusters and clusters and clusters. So you know what I'll do now? At step 2, I won't select 4. Let's start by selecting the largest distance for merging the nearest 2 points. So then you invalidate your cluster principle. The similarity measure is complete linkage, but the clustering protocol is always about taking stuff together that is at a small distance. Okay? So there always you will go to the smallest. So here you see that happening. Under complete linkage, you still select the smallest distance here, you still select the smallest distance here, and here you would, but there's not so much to select anymore. Okay? You take the 9. Yeah? So, that's important. Okay, so these are two extreme measures, you might say, single linkage and complete linkage. Have you got an inkling of what could be somewhere go in between? Well, we'll get to it. Alright, so, as I said, most research, most science, you start with a table. Sociologists who interview people, what do you think about this? Do you feel, what kind of pain do you feel on the scale of 1 to 10? And then you do this, and, 8, that's very good. So, that's... those kind of things happen. So tables are important, but within the framework of this course, we'd like to use sequence alignments, multiple sequence alignments as a widely used input in genomics. Yeah. And what do you need to do? You need to convert that sequence alignment into a distance matrix, and you've seen various ways how you could do that. Yeah. So it's the same thing really. Okay. So we'll do a few more methods, but really more when we talk about phylogeny. Yeah? And so I'll give you a bit of easygoing theory. Phylogeny is a bio thing, right? Biologists are very interested in phylogeny and species and relatedness between species and so on. So they will not talk about graphs like computer scientists and nodes and edges and stuff like this. They say, no, this really looks like a tree to us, right? And a tree has leaves and, you know, and branches and stuff like that. So they talk about that. It's the same thing, really, but it sounds completely different. So here you go. They call it also nodes. You know, they don't like it, but they have to. So an edge and node. So, you know, we're sort of here in between. But don't, you know, you see those two communities choosing their own type of. So, basically, easy. This is a leaf node. Sometimes it's written like this. Sometimes they write it with VE. You see that both happening like this. So this is then an outer node, you might say, right? And this is then an internal node, because, you know, it doesn't communicate, it has more connections, so that makes it internal, right? Outer nodes have only a single connection into the tree, and internal nodes have multiple connections, 2 or more, into the tree. And you see, by the way, 3 sorts of species that might be interesting, you know. Fugu is a much pestered fish in the meantime, because it seems to resemble our genome a bit, so we do a lot of experiments. Drosophila has always been maltreated in this world ever since it was considered interesting enough to biologists. And then we have mouse. I don't know about that animal. Okay, it's eaten by cats, I think. Okay, anyway. So another thing is, these leaf nodes are very often also called, don't get angry, I didn't dream this up, as OTU, meaning an observed taxonomic unit. The idea is that these guys are around, and these guys are ancestral. These internal nodes are normally ancestral nodes of sort of old in-between organisms that normally will be, you know, gone extinct, right? So you might not see them, but the leaf nodes should be observable, otherwise they cannot be a leaf node. And that's why biologists refer to those also as OTUs. Yeah? And in Holland we would say otus, of course, right? We do that. Not so much anymore. We start finding out. Sounds even more horrible than the things before. Anyway, and now it's interesting because, you know, if you think about what's the oldest guy on the planet here, which of the 4? Or where is time? We know there is evolution, so where is time? So if you start thinking about that, you get to the concept of rooting a tree. Where did history start? Can we make a timeline? And there is in fact a surprising way of making a timeline. For example, if you would just say, and we'll get to that, how this could be decided, where it is, that you say, you know what, point 0, t is 0, for me is here, along this branch at this moment. So what can you now do? You grab the red dot by your hand, and pull it out of the board, and see what follows, and then you could get this picture. See that? So you don't change the distances, right? That's the idea. So now at once you can see, hey, now we can talk about a timeline that runs from time 0 till the very end. And maybe those leaf nodes are the currently observable species, the OTUs, so they should be latest in time. And here you see that indeed these internal nodes started coming about earlier on. Let's see, right? So it starts making a bit of sense. And then the question might be, in how many ways could you place that root, you think? 5, yeah. Now, that's a very good answer. I see where you're coming from, but you could even now make it finer. How many ways? What if I say the 0 point, oops, sorry, you know, if I would put it here, I call that another way. How many ways now? Very many, right? It could be anywhere along those 5. But 5 is a very good answer. I like it. Okay. And if you want to read, by the way, it's also in Durban. Although probably explained by means of hidden Markov models, but anyway, that's what Durban likes to do. Alright, so how to root a tree now? So one way is, that's what biologists always liked, and for 20 or 30 years that happened most of the time. Suppose we would have not had, which one is it? Drosophila. Okay, so suppose we would have done this experiment without Drosophila. So we would have had this tree, right? Drosophila is not in the experiment, so it would have looked like this one. And now you say, you ask the biologist, how should we root a tree? And then the answer is, you know what? It would be very nice when I find another species that is there today, but that I can be relatively safe about that the split between this new guy, and the ones we had, must have happened very long ago. If that happened the longest ago, if that would relate back to the common ancestor of the whole group, with this new species added, then we have something. And that is the idea here. And this is outgroup theory. So in this case, this is now the D of Drosophila. So the claim here is if Drosophila is really very distant from the others, mind you, it should still be homologous, the sequences, otherwise there's no comparison. So an outlier, but still homologous, a divergent homolog, the most divergent homolog, then you know that it should cluster like this, that this one should be added outside the subtree that we would have had without that outgroup. Okay? So in that, you can say, that means then that the root of the tree should be along the branch that connects Drosophila, the D here, to the rest of the graph or the tree. Okay? That's one. But suppose you can't find an outgroup, you need to do something. So what do you do then? Then you could, that's another way of doing it. You could say, you know what, not knowing so much, but here I just filled in for the sake of it a couple of distances. And you could say, you know, if I don't know anything, I could at least look in the tree which are the most distant organisms, right? Which two are at the greatest evolutionary distance? Can you see what that is? Is it, what is it here? Which distance is the largest? I do one for you, you can fill in the rest, okay? I'll do an easy one. I only need to add up two numbers. And if I'm interested in the distance between Drosophila and Fugu, the D and the small f here, then I add up two distances, distance 5 plus 3. I get to 8, correct? Okay, now you do from Drosophila to mouse. What do you get? 8. Or from Drosophila to human, what do you get? 8 again. But what would that mean? And the idea is now, okay, not knowing anymore, what you could do then is say, okay, you know what, I put a midpoint exactly in the middle of this longest road between these, the most widely divergent species. And really, then you say, oh, now we have a problem, because, you know, it could be in between these guys, or it could be in between D and M, or it could be in between D and H, but if you look carefully, you'll see it doesn't matter. That point would land here. What is the distance here between D and this point, you think? Now I want to hear something. I see fingers. I don't hear that's good enough. 4 fingers is good. 4 is the answer. Good. That's cooperation. Okay. And you see that the remaining one, if this is 4, then this should be 1. So 1 plus 2 plus 1 is 4. There again. Okay. So you're really placing the root in the middle of the longest connection, so to speak. Yeah. It's another trick. And later on, I might ask you the question, what is this method doing actually? But, okay. And another one is, well, we've talked about this before, about globins and orthologs and paralogs. You remember that tree? So you could do that theory and then say, oh, okay, so biology, if you have that, you know, if you know where paralogous genes are, then you place the root in between paralogous genes, you know, speciation, duplication, but then you need to know about the biology, right? So in general, when you just have a bunch of species you don't know a lot about, this method can be applied less frequent than these two. Okay? So if you know nothing, you do this. If you can find an outgroup, you do this. And if you know even more about paralogy and orthology, you can resort to the more bio-type methods. Okay? And if they all agree, if you do them, they will be all the nicer. Right? Okay, 3 possible ways of rooting a tree. Okay. Biologists, they like to fight. If I didn't tell you a story about a bitter fight, you know, remind me, okay, before the end of the lecture. To convey a piece of history to you. Anyway, but, you know, there have been fights about this as well, because in early days people like to fight. I think on this planet it's going much better. You get all these doom stories. People fight less than centuries ago. And even less than half a century ago when it comes to science. So you could call it quick evolution. But anyway, so you had the cladist against the phylogenist and against the parsimonist. These were all bitter fights, sometimes physical fights. And I've seen ones in my life, but I'll talk to you about later. Okay, so cladogram, so what's the difference? You know, you see here, one is, you know, the cladogram is unscaled. So these length of the branches don't do very much. You know, you know, you can see the topology, how things connect together, but these distances should all be taken with a big grain of salt here, because they don't move. Here, when you have distances defined, and oh, this is 20 million years, and this is, I don't know, 25 million years, then you don't talk about the cladogram, but about the phylogram, okay? Just so you know. So this is what biologists do, they like to give names, as you know. Yeah? Okay, so scales in phylograms. Okay, how many trees are there? Well, here you go, simple formula. Again, this is faculty, right? And here, so you see sort of relationship, but I'd rather show you some numbers. So how many possible trees are there? Unrooted trees with 10 nodes. You're at 2 million possible trees. That's for unrooted trees, and if you want to root them, that's a lot more, because now you can take this branch and root them, and the other branch and root them, so you get more possibilities. So there are 35 million, roughly, for 10 nodes. So you can imagine what it will be if you have 50 nodes or something. Just calculate all trees, pick your nicest one, forget it again. We're in bioinformatics, these things are normally not possible. Okay? And here is the picture, and you see the type of growth, sort of exponential growth. Yeah? The number of trees versus the number of nodes in either of these trees. Yeah? And do you see something interesting? Well, you see it more clearly here. Do you see? Yeah? One is following the other. That's a nice coincidence, isn't it? Is it a coincidence, by the way? You think about that. Okay, here you go. You see them following one another nicely as well. Yeah? All right, so how do we build a phylogenetic tree now? First step is maybe the most important. And here it's, there's remark, choosing a molecular marker. What is that? A multiple alignment of some gene set. And then if you want to do that, what genes would you pick? Or take all genes, take the whole genome, but then you have to sequence the bloody thing. And then making a correct alignment of a complete genome is a very difficult thing to do. So maybe it's good when you would have a good marker, in the sense a sequence or something that represents each of the species or nodes in your tree well. And what would that mean for sequences? Would you take the histone family as a good marker? That's a totally invariant. It's totally conserved between bacteria and human. So what do you see about those sequence alignments? That's easy. But all these sequences are nearly identical. That's not good. You get a very flat sort of tree. So you need families basically that are still alignable, but have as much variation as you could possibly have in order to get a differential view. You should get different distances. If they're all the same, the distances, then it's all boring, right? You need differences, but still alignable. That's basically a good molecular marker. Well, if you have a set of sequences, you perform a multiple sequence alignment. That's maybe the most important step in terms of quality of your procedure. Then you might, depending on your method, choose a model of evolution. For example, as I explained to you earlier on, to correct sequence distances, correct them by modeling it according to some evolution model. Then you need to choose a tree building method, say a cluster method, but then one that is amenable to phylogeny. And then, of course, you become a biologist because you make a tree to do something with it normally. So assessing the tree, learning from it, of course, is also very, very important. So, here you go. This was a very good marker set. I mentioned Carvesi the last time, the man that was ridiculed so much and attacked so much when he talked about the archaea bacteria. But he also came up with, and he did that because a bit earlier on, he had found that 16S ribosomal RNA sequences are a very nice set of sequences that are alignable because they have fragments in the sequences that are nicely conserved, so they can act as islands or markers in your alignment, as anchor points, and in between it's very variable. So you have both worlds. It's alignable and it has variations, which is nice. So most studies indeed still are with this bacterial chromosome, bacterial gene. Yeah. And then some of you might ask, bacterial gene, what about adding higher organisms to the pack? What do we do there? Is anybody an ID? Do we have bacterial genes? I see. Is there any cell organelle you know that has also DNA? Mitochondria, very good. And of what origin are these? Bacterial. So that's how you can get to add sequences to this pack. Okay. Right. So this is old stuff, so I'll go quick. This is just your back mutation. So there are these models that you can use to understand timing along the path of evolution. And so the saturation, you've seen these sort of curves that after a while the real evolution is not observable anymore. You would need a model to stretch it over that. And so here are all kinds of models like time distances and so on. So this is all done. So, and these slides might even be this slide that you saw earlier on, how it works. If you fill in 0.3, you get a corrected distance of 0.38. So these models show you indeed, if you observe something behind the screen without you knowing, more evolution really has happened. Yeah? And with both of these models, you get that effect. Okay, so I already told you then, and I will maintain that statement, that these correction methods are really not so widely used in most modern methods. They take the data as it comes. Okay, there are three main classes of phylogenetic methods that I will run through with you in the remainder of today's time lecture. So, three distance-based methods. We've done most of those, luckily. And then we get into the fighting lot, character-based method, subdivision in two, distance and character-based. But the subdivision under character-based is two main classes, parsimony methods, maximum parsimony, and another class of methods that you've seen before in other guises, maximum likelihood. Yeah? And even Bayesian will be part of that. Okay, so let's do the first bit, distance-based. Look, this is also the most unfortunate name-giving ever in history, I think. But okay, so I asked you before, we did two cluster methods. Remember, single linkage, nearest neighbor, complete linkage, furthest neighbor. Is there anything in between? And then it's a Monday, I know, but I would have hoped that somebody, you can't do this, it's not so easy with your fingers. You might say, what is in between max and min? Give me something. Average, for example. Brilliant. So, see that word coming back here? Yeah. So this is, unweight. This is a method, and it's an in-between, and I'll show it to you in a moment. But the authors, Sneeze and Sokal, they were great friends. They've written a whole pack of books, and when it was Sneeze and Sokal in one book, the next book would be Sokal and Sneeze. And they were real friends, so that's how they did it. And they were statisticians and biostatisticians. So they've coined their method, unfortunately you might say, unweighted pair group method using arithmetic averages, and they use these UPGMA, and you can imagine how a Dutch would pronounce this, with the full G sounds, of course. Upma. Most horrible sounding phrase I've ever heard. It happens. So please call it UPGMA when I'm in the area, okay? Anyway, so there you go. And then even I skip that A because they like this kind of. Again, so here we go. Looks horribly complicated, but I'll talk you through. You know what this means? So you have 4 points in this cluster. You have 3 points in this cluster under the assumption of single linkage. What would the distance be, you think? Nearest one. Shall we say this guy here? Is that the shortest? Let's say yes, yeah. And what would be the maximum distance? Something like this, or maybe that one, don't know. You have to measure it. Something like that, okay? So if you want to go in between, the idea is take the average. How would you calculate the average over all of those distances? You take all of them, and there are 4 times 3 of those distances. And you know how you calculate an average? You add up the values and you divide it by the number of values you have, and that is exactly what you see here. So this horribly complicated looking formula is just taking an average, okay? Which is done many times in life, of course. So, and this is the example. So this means this is the dimension, the number, in other words, the number of points in the one cluster, the number of points in the other cluster. So here is, for this example, 4 times 3, and this is just the addition over the 4 and the 3 points of all these distances. Okay? Right? That's how we do it. So if we use that and start calculating, what do we get now? Oh, this is another way of doing it. It's the exact same algorithm, which I will go to that I showed you before. But this is the way, what they say they will do, and it's basically exactly the same. There's only one difference that you see here. Now, before, but I won't go back. I'll show you when done there. It's easy. Here we go. This is the same data set as before, okay? So we do the algorithm. What's the first step? It's boring, I'm sure, by now. the nearest 2, we don't need to calculate yet, so that's our 4 again. But now look, what did we write before? The distance between B and D was at 4, and on your early slides I would have connected the 2 here. Now, that's the Dij divided by 2. Biologists say, you know what the distance between B and D is? That is this branch plus that branch. And that should be 4. So what do? You shrink the whole thing. You have the distances, so to say. So if you put it at 2, it means that the distance between B and D is 2 plus 2. Okay? That's why this distance divided by 2 comes from. Yeah? Why you let them merge. Okay? Here. Another warning. Don't forget that. Okay, so look at this. So now you explain to me how the hell could it be that you get 7.5 as a distance between C and the pre-cluster 2 nodes BD. Some average probably between which 2 numbers? Are you all in the clear about this? You look up distance. What is it again? CB and CD somewhere here, and probably you've got something like 7 and 8 or something. And, or 6 and 9, is that possible? What is it? Let's do it. Now BC, CD, BC, 7 and 8. And the average between 7 and 8 indeed is 7.5. There you go. So you do this, and then apparently the distance between C and BD now is still a nice round number. Why is that? CB equals, it's always difficult. Here, 6. How would that be? CB 7. And the other guy then should be, what is that? AB, right? It's 5 indeed. Average between 5 and 7 happens to be 6. So we're fine. Go back to step 2 again, take the smallest 6, and then here you see, that you get to 725. Why is that? This is the distance between cluster AC and cluster BD. So which 4 distances do we average here? The distance AB, AD, CB, CD, all possible distances, right? Do that, divide them by 4, and apparently you get to 725, 740. So here you do, faithfully, you go to all these distances. The 6 is easy, the 3 here now, and then here you stay consistent. This is here the distance, the place of the split point here is at 7, is at half, 725, which is just over 3.5. Yeah? Okay. Let's do one. Let's take another example. This is from Essential Bioinformatics. See what happens. So basically we do the same thing. This is the input matrix. But what will we do? We'll test how this tree, how faithfully does this tree reproduce these distances. If the tree would be spot on, you should really find those distances back. Well, that always happens. So here we go. I'll talk you quickly through it. This is a set of distances for this example. 0.35 is the smallest. You make the first split, AC at half 0.35, that's here. Take your next step, here it's all really calculated for you. The remaining ones, you divide it by 2, that and that and that, so you build up the tree. And in the end, you'll have this as the result. Just the same as before. Now I'll plot. So, what's the distance between D and A? D and A. Or I say it otherwise, this is very confusing to you. A and D. Of course, you should never say D and A if you mean point D and point A. Yes. All right, okay. Who can tell me the distance between D and A? Anybody? Add up all these distances, but I'll give you a trick. This long one, right, what is that? This divided by 2, so this guy is long, so if we thought this is then the distance, you see? Clever, eh? The answer is on the slide. Basically, you add up all the branches, but if you want the distance between A and D, you bet that is just 0.617, because this branch length is 3.09, and that means that this plus that is equals to, of course, the same, because all those points are at a nice straight line, right? So it has to be. Okay, now then, this is the, so if you do that with all of these distances, so 6.1 here, what is it? Oh, they rounded the numbers, okay, 6.2 it became, let's forgive them. But this was the original input. What's your conclusion? How cracking good is this method? 0.35, yeah, okay, that's where we started, so that remained in place, okay. But the rest, you see, different. In this case, not totally different, but still, here, it's here. Oh, this is not so good, right? This is the largest error, perhaps. Well, the conclusion is the values are not the same. So this method, UPGMA, is not able to faithfully reproduce in its cluster building the original distances. We're in trouble now, right? What can we do? Another method? Change the data, what can we do? You know what happens when what you need to do if you're in trouble, in this kind of trouble? Talk to either a statistician, and this guy doesn't know, you talk to a real mathematician, okay? See what they come up with. So here you go. These guys are, they come even with some biospeak, and that is the concept of ultrametric distances. So metric, as a metric, is a way to measure, and if you're ultrametric, you're even measuring more, you might say. And that is the sort of theory. And it relates to biologists who can talk about this, about the molecular clock. Do you remember the old Dayhoff matrix? What was the assumption about the evolutionary speed there? You remember if you have a PAM1 and you want to make the time twice as long, what did you do? You multiplied these matrices, but what's the underlying assumption? That the speed of evolution is not changing. The clock ticks uniformly. Is that true? Don't know if I told you. Stephen Jay Gould came about. He wrote many very good books, generally about science, but molecular sciences especially. And he came up with a theory of punctuated equilibrium. That's a difficult way of saying, evolution. A disaster happens, all species are adapting like crazy. So a lot of evolution. The clock ticks fast. Then it's, it's all smoothing down, and the clock ticks slower, and then something happens again, and you get quick adaptation. So the clock is certainly not uniform, and that means that is not true. And even maybe in the same period, some species evolve faster than others. So at the same time, in different lineages, the clock might tick differently. So that's a bit of a problem. So under the assumption, biologists, the first ideas about evolution, you always start simple, was, there should be a uniform clock. It's easier. They all thought that and others didn't. So what do you do if you have a uniform clock? Then, well, basically, under that condition, I'll get back to this, UPGMA works well if the planet ticks uniformly. We know it doesn't, right? In the meantime. But under that assumption, it will, and here you see the red dots here, it will horribly fail if the clock is not ticking uniformly. I want to show you a picture. This one first, that's very nice. Okay, so if a clock ticks uniformly, what have we got? We have a common ancestor, and we have all of these leaf nodes, right? These observable OTU species. What do we know? They're all now here. If they all came from the same common ancestor, we know that the same number of millions of years hold for each of those leaf nodes. If the clock ticks the same way, they all evolve, they all build up the same number of mutations, all nicely uniformly. And that then means if you make a tree, they should all be nicely aligned like this, because the distance from the ancestral node to each of the leaf nodes should be identical under the assumption of a uniform clock. Yeah? Does that make sense? And if that assumption doesn't hold, bacteria, they evolve much faster than humans, for example, because they have a generation time of 20 minutes, and the humans that's roughly 20 years, tending to go up in some parts of the world. So even slower. So then you get sort of trees like this, where this nicely, aligned line of edge nodes, of leaf nodes, is not maintained anymore, and you get this sort of stuff. Right? So this is real world. This is bio world. Well, it can even be more nasty than this, I can tell you. But this is not so realistic, perhaps. In most cases, could you use the model of uniform clocks? Well, what about if you talk about, clustering monkeys, apes? You might say, okay, now, but when we talk about evolution of 4.2 billion years, now we talk about 1 million or so different. Let's call this uniform. You could, approximate if it's close enough by the uniform model. Okay, anyway, let's go back now. Because I said, talk to a mathematician, and then when you do this, you get mathematics speak back, there's no other way. So here you go. There is an assumption, and that is called, this mathematician trees will look ultrametric, look like this, under the assumption of a uniform clock. And then there is something that is called the 3-point condition. And the 3-point condition reads like this. How was it again? If you have the distance between y and j is smaller or equal to a distance I to a third point from I and j to a third point. So meaning this distance here is equal or smaller than these distances, and these distances are always the same. So if you do this, you see a plus a, that's this, you get from I to j equals a plus b and a plus b. What do you see under this tree? If this is a and this is a. Do you see a fork? Could you eat with this thing? Yeah, it's nice, right? It has the same, so you can sort of stick it in some meat and pick it up, right? So this is a well-behaving fork. And that is always what you get under this condition. Okay? And if you have this, then if you have all points in a matrix, all distances are organized like that. So meaning distances between two is equal or smaller than distances to a third point that are equal. Okay? Let's see. Let's go back to this example. This was the input. So basically, what do we need to see? We need all the time to see. I do it once again here. One distance smaller than the connecting. This is a triplet point. We talk about point I, j, and k here. Yeah, 3 points that have this relationship. One small, two larger, but the same. Do you see those triples? And all triples should be that. What is about ABC? What do you see there? Points ABC. How do they relate? A to B, 0.42. A to C, 0.35. So A to C, and then C to B, 0.42. Do you see the triplet here? One smaller in the pack and two larger, but the same. So if you do this for all these points, you'll see that this condition, the 3-point condition, is maintained here. Right? But this was the original matrix. Do you see that condition here? Are there triplets? Well, the answer is no. So the original matrix is not ultrametric. It's something more nasty than that. And that is why poor UPGMA works under the assumption of uniform clock. So it beats the data, so to speak, into that form. It can't do anything else. It stretches those, You thought you could be 0.55, but now, you will make a wrong tree, so I'll bend you into 0.62. Question? Yeah? Yeah, do the I and the j always have to be the roots in the... No, not the root. It should hold for all. The forks, or... You always get that situation of a fork from those three. Yeah. But that's what happens in a tree. So it's always binary trees. You don't get trees with multiple forks. Yeah. But can you switch the indexes around? Does it still have to be? Yeah, true, right? Or yeah, that condition should hold. I don't exactly know right now what you mean by shifting index. If you just call I, j, and ji, that doesn't matter. Do it like this, and then you switch it around? No, then it doesn't hold. No, then it doesn't hold. No. Okay, so there you go. Now, this is the uniform clock assumption. So UPGMA needs ultrametric distances, uniformly ticking clock to be able to do it faithfully. Otherwise, it will go horribly wrong. Okay, I think we should take a cup of coffee and then I'll go to an even one other formula, and then we have had most formulas for the day, I think. We go from a 3-point condition to a 4-point condition. Yeah, thanks. Do that.
Read on. That will teach them a lesson. You're recorded now. First announcement. I should apologize in the sense that on Friday I promised to 2 or 3, maybe even 4 students that I would put the example online, which I forgot to do over the weekend. I'll do it tonight, and if I forget once again, you send me all an email tomorrow morning. That will teach me a lesson. But anyway, I'll do that. Word on the exam. In earlier years, I would ask 2 times 5 questions, open questions, 1A, 1B, 1C. You had to work out a little algorithm or ask, or more biological. So I would have 5 basic questions and 5 advanced questions. So with basic you would have, you see students who do basic very well and advanced, not, and there are other types who didn't learn so much, I think, study so much, and they're better at the advanced. So that was always interesting. This year, however, the scores are a bit larger, the group. It takes me half an hour to do an exam. Times 100 is time. Too much time, right? So I need a trick. I need you to self-correct your exam and mail me the result. But, people in the main tower don't allow these creative solutions. Or you correct another person's exam. How about that? That's good too, right? You're not sure about the outcome, if you say. It's tit for tat and all kinds of... You get game theory if you start doing it. So that I have to do it, guys. And that means that for bachelor exams, I sometimes do multiple choice questions. So I think what will happen is I'll do the basic part in multiple choice. And we found over the years that there is a very good correlation between multiple choice blocks and open question blocks. So I'm certain that I'm not maltreating you in any sense. It's for you maybe quicker. You know what? For a poor teacher like myself, preparing a multiple choice question is a lot more work than an open question. Give me the definition. That's easy. You write it up. As fast as you can type. That's it. But the multiple choice is 4 things where one is sticking out and the other should not be plain nonsense, right? And it should be understood. That's a lot of work, right? So anyway, so it's more work on me, but I hope to earn that work back in, when it comes to marking those questions, because I could give it to my son, for example. Anyway, I didn't say that because that's not allowed.
No.
Is it on?
Ask Jose to...
So could you switch back and take that off? I said I could. I didn't say I would. Or will. Right? Okay. So what I will do, I think I'll select an exam. Last year, the year before last, we'll see, as it was with 5 times 5 open questions, and I'll do a couple of multiple choice questions from bachelors, but you get a feel of, how I tend to do this, right? To give you a feel. Yeah? I'll select a few questions that are on alignment and see how that would work for you. No, I think you're well prepared. If you sit, so the slides are leading, right? Books are very nice, but it's to deepen your understanding and so on. So, if you get all the slides, you're perfect. If you don't get it, you read your book. And then if you don't get it, you come to me. That's basically the strategy, okay? Yeah?
In internet, like there's something scheduled for Thursday. What is that for? It's a seminar for this course.
I think the boys do... That was announced, but now I forgot. What Jose told you. I think it's a working group. On Friday, there is a big demonstration, a national demonstration in The Hague, because the government's all the time promising money and at the same time taking money out of the education system. So people are sick and tired of that, so they want to show that. On Friday, the VU board supports the trips for students and teachers to The Hague. So anybody can go. I decide to serve students who want to be here on Friday. I've walked the last demonstrations and so on, so I'll stay here. So people can come, but the working group is more important for you to finish, so we decided to put that to Thursday. Now I'm not sure whether that's for everyone or only the ones that we should work out. You'll get an announcement of the exact rule if that is not clear. So what you've seen so far is not really clear whether there is something on Thursday and Friday or only on Thursday. Is that clear to you? No? Then you should be instructed. Okay. Anyway, good. I'll ask Jose to put a clear message online for you. Okay? So, quickly back to all of these phylogeny methods. So, I started alluding already, ultrametric spaces. You have these triplets of numbers that fulfill this 3-point condition. If that is the case, your set of distances is ultrametric, meaning that simple methods like UPGMA can do the job. If the situation is more nasty, more difficult, more biological you might say, more realistic, then UPGMA will not be able to do the job. It will make errors. Of course the branches will go wrong, that's one way. Branch length will go wrong, one way of making error, but even the topology of the tree might change. That's a graver error even, okay? So it goes pretty much wrong. So then there is another notion. That's the next step. So here all distances are basically, or the distance between any leaf node and the root is equal under ultramatic distances. Here you see that's not the case anymore. You know, this nice straight line is not there anymore. So this species has evolved faster. It's at a larger distance now from this split than this one. And here it's the same thing that you see. So that nice line is not there anymore. But still, there is one other condition that comes in, and that is that any distance still, under this assumption, the distance between here and here, although they are the result of different evolutionary speeds in lineages, still the distances are additive. So that means if you want the distance between, evolutionary distance between this species and that species, you add up this length, this length, this length, and that length. Once again, these lines do not mean anything. That was just for old computers to be able to print stuff, right? Here I have it, I don't know if you can see it. This tree here is like there. And this is the one that Darwin would draw, sorry, Ira. Yeah? So this is the same thing. So these lines do not mean anything, right? Distances are in this direction. There is one slide showing you, but just to remind you that this is the case. Okay, so let's see what we can do. And so, what are additive trees? These are trees where the distances between any pair of leaves, and there, and this and that, and so on, is the sum of the length of the connecting edges. Yeah? And then, if such trees obey the so-called 4-point condition, they're really additive. Now, I showed you the 3-point condition. Now we get the 4th point. There we go. Here it is. It looks like that. There's also an equality there. So now it's not one thing being smaller equal than two things. It's now 2 times 2 things here and 2 things here compared to the last one. So the distance, dij is this distance. And we talk about this distance here, dkl. You see that? That's here. This guy plus this guy plus these distances are smaller or equal dik, which one is that? That's here. And up again. Plus djl, what is this guy? That's that. Down, down, you see that? And that should equal dil across plus djk is across again, but then from bottom here, up top there. See that? So this should equal each other. What does that mean? That somehow these distances, they keep in check, right? When does the equal sign start to happen? By the way, who's quick, even given it's Monday? Which branch length should have a very small value to make equality here? M, I heard the word M, yes. So this guy is 0, meaning this point merges at that point, then you have, yeah, the limit case at equality, okay? So it's a very nice, mathematicians like this type of formula, yeah? So if this happens for quartets of points in your similarity table, you've proved that your set of points is additive. Then we can still make a tree with another method that's important, with another set of methods. But for historic reasons, I do one method that's called neighbor joining. Okay, so what can you do if there is still additivity? Now, this is what I said already. So you can still construct a unique tree. So that's nice to know, that is possible. And here you see what comes from additivity. Basically, you average out. If you have a set of distances, the distance between I and M, if you have the distance between the point J and M, and you have the distance between I and J, here, then you see you can build a fork with these distances. And now you have this condition, the distance between K, and that's nice. So you would like to put this point in now. And the distance between this internal point and M you can calculate using this formula. Right? And you see that that must be correct.
if you have these things. If you compare this fork with the fork I asked you, can you eat with this fork, the question before, what do you say? Which is better for you, for eating the meat? This one or the other one? This is a more inconvenient fork, right? Why? Because it turns out that this branch length here is shorter than that one. But that is what we want. The clock doesn't tick uniform. There is no necessity of a clock ticking uniform. So we want to be able to do this. So basically you average out over these distances. You say that should still be added up, and then you can do this trick. And then it means that if you have these distances, you can calculate the distance C, and therefore you can also calculate A and B. So the algorithm, you can use this to construct an internal point if you have these three distances. IM, JM, and IJ. Right? There you go. Okay, here, if you have time, enough time, you know, study a bit less for your exam, do this, more fun, right? Then you can say. So, what's the statement? If you're ultrametric, then you're for sure additive, because, you know, under the ultrametric, of course, you have to be able to add up the distances, but not the other way around. Eh? So, additivity is a wider class than ultrametricity. It's a contained Venn diagram, if you like. So, how would you prove this? So, basically, you take the additive formula, you fill in what you know from the 3-point show, you fill in the 3-point condition in the 4-point condition. Somebody wants to ask a question? Yeah. So, I told you about Smith, Mr. Smith and Mr. Waterman, who became, you know, pretty famous overnight by putting in a famous zero, right? These guys did a bit more than a famous zero. They had to change a few more formulae. But anyway, neighbor joining really, you know, was shaking the community at the time. And it was the first method that you could just run, get a very good phylogenetic tree. And after all battles that had been there, everybody was tired. People were very happy that now there was a method that anybody could embrace. Yes, it was a distance method, so the other guys didn't so much like it, but they couldn't avoid it. This was a good one. Basically, neighbor joining is a method that guarantees to produce a correct tree if the distances are relative. We'll go into that example that we did before where UPGMA fails, and you'll see that this guy can do it. And so it's a global measure. I allude to that in a moment with a figure to give you the feel. Basically, why is it called neighbor joining? At each step, it's doing this trick. You have these distances, and with this formula you can place this root point in between any of the pairs, and if you can do this, you can build a tree. But I'll show you that when we get there. So basically, what is a big problem with neighbor joining? Fundamental problem is it needs all distances in the tree. But how many of the distances do you have when you start building the tree? You've seen how it goes, right? You take the first 2 points together, and then you have a distance, and then you take another point, you calculate, and then you have... So you only have all the distances in the very end. But here, neighbor joining demands that, no, we start with a tree, any tree, doesn't matter, we need distances, and then we adapt when we go, and we convert that tree, that starting tree, into a real correct tree. So we need a set of distances. And what is the thing? Let's see if it's on here. So that's an unresolved star tree. What is happening? And I'll show you that in a figure. We start this is a funny method. It starts as a fake tree, and it unfakes the tree as we go. Fake news, fake trees already by then, you know. But here, the fakeness is resolved as we go, and it will be a correct tree in the end. Yeah? You unfake the tree, and I'll show you the tree how it looks. It's called a star tree. Okay, so there are a couple of formulas. Basically what it's doing, UPGMA couldn't do it. Neighbor joining corrects distances between points, keeping the eye on the complete set of distances. Now, see if I can give you a picture of that. Here we go. If you know nothing, so this is an example of, what is it, how many taxa? 7, right? 7 points. You start with these 7 points. To leave notes here. What do? You can always calculate the average point between those points and make a star tree just the average point. So this is what people refer to as a star tree. It's just, you calculate that point as the midpoint between each of those, and then just fill in the distances to each of the points. So this is how we start. And now we're going to do what the method implies, neighbor joining. We now want to join two of the points. And how many pairs of points are there? Well, quite a few, right? These two, or these two, or these two. All possible pairs you can calculate through. And then what do? You merge points and see what happens if you take, so this is probably the example that these 2 points were selected to be joined. Then you do that what I showed you. You make this inappropriate fork, the uneven fork, say, with that formula, and have this. Yeah? And what is the ID? The criterion is we have a total set of distances here, the total tree length, right? And we choose over all possible pairs the one that will lead, if you do this, to the minimal set of overall of added distances. What do all these added distances represent, you think? If they're very long, what does that mean? A lot of evolution, a lot of time, a lot of mutations, right? So what are you on for? You optimize minimal evolution. The concept is, if you don't know things, your model is probably best if you minimize evolution, right? I'll get back to that point and I'll explain Occam's razor with an example. But that's so overall. So basically, how does this method proceed? It checks all pairs, then selects, this is the best one, does this, calculate this using this unequal fork formula that I showed you a moment ago, right? Where you can calculate this distance and these distances. And now it says, right, we're done for this bit. This is all still fake, so these lines are the fake, the uncertain distances. You do this, so now you're sure about this, that's done. And you say, you know what, I put this on a piece of paper on the side, and I'll represent this subtree by point X. So red goes to the side. It's done. We have this stuff now. We put it aside, and we go on without the red lines. Only point X. And now we do, so that means now we have these points, and this X point, do the same thing. Join two neighbors, the best one that lead to the minimal total branch length. And maybe that's this one. So you do the same thing, this goes to the side list, and you go on with this tree that is only black and these points. You do the same thing. So now maybe these two subclusters are joined. It could be, like here. And then you go on, so you go on, and the dimensionality reduces, and here you have your full tree. Yeah, in the end. So this is how it works. By joining all the time two former points, you cluster them, you might say, but you represent them by their ancestral internal point, and then you go on and you stop when you're done. Okay, so that's the way. So this is a formula that you saw before, and these are conversion steps. So you have this distance between dij. You make a transform distance, if you like. They call it a corrected distance, where you add in the distance between point I and all the other points, and the distance between j and all the other points, because here's the definition. Yeah? Ri means you just sum all the distances between point I and all the other remaining points, remaining points here. And these points could be leaf nodes or internal nodes in the algorithm. Okay? So, if you do this, then you are sure that you get at the end a tree with minimal overall distances. If you want to really find the proof, then you can start reading in Durbin, but it's not required to be able to reproduce the proof on your exam. Okay? Okay, so here you get the algorithm then. There you see this statement back that I showed you before, the unequal fork here. And you see here that you get these corrective steps here to be able to get it right. So I give you a feel by taking the example of a moment ago for UPGMA, and we run through this with all these formulae, and you see what happens. Here we go. Same input. Trust me on it. You can go back. You can do that at home. Here are these formulae that were on the slide earlier on. So here you see this concept. We have this R, the distance from A to all the other. So that's distance AB plus AC plus AD in this case. So RA is just add up all these points. And then you get this transformed. This guy here, you just divide this by the number minus 2. Meaning there are 4 nodes here in all. So your corrected RA is RA divided by 2 in this format. You do this for all the points. So you get this corrected RA. which you start using and fill them in here. Now you see, you get these distances now. So now we just start clustering. But are you shocked? Are you a mathematician or biologist? Right? Negative distances, bloody hell. Terrible. Go home. Weep bitterly, you know. Course is over. No, the biologist comes to the rescue in this case. Guys, what was the thing that the algorithm wants? You just look at this, select the smallest one. Let's do it. Who cares? So yes, you select here. And now you have a choice, you know, this is the smallest one, minus 105 or minus 105 there. Just with all the other clustering methods, if you don't know what to do, just pick one, eyes closed. Finger goes to the paper, and the one nearest you select, okay? And so this is what you do. So if you do this, you now have these filled in distances. Looks a bit funny, I admit it, but this is live at the moment, okay? So now we go on. What do? We tend to select, I think this one will be selected. Here we go. So basically A and B are selected, and all of these calculations and correct the distances. Here you get that the trick of the unequal fork. There's that formula I showed you a while earlier. And then you see indeed, the point U is now this new internal point going into the tree, and this is the unequal fork. It is this sort of average calculated in this way between A and B. Yeah? So, and it goes on. And these are now the recalculated distances from this midpoint. So where are we in the picture? So we are here now, we've calculated this point, it's unequal. And now we are only interested in this distance here. This we put to the side, and we go on. That's here. And here you see the recalculation of the points to the new cluster, U. Okay, so again, negative distances, who cares? You pick the smallest one, being, you see it in gray, it's colored in the book, but this is the smallest one here, right? And you go on with that one. So that means C is added to the pre-existing cluster joint neighbors U. C is added to this pre-existing node U, representing, of course, the neighbors A and B. You go on, you do the next step, they're done. And that's another important point about neighbor joining. It's an unrooted tree. UPGMA, by definition, gives you a rooted tree. This method gives you an unrooted tree. So you would need to root it by midpoint routing, outgroup, or the biological way that I showed you before. Now, what is the distance between D and C? It's Monday, I know. Come on, you can do this. 0.55, right? And what do we need to do to get D to A? Add 0.4 plus 0.5 plus 0.15, 0.6, something? Okay. Anyway, here is the thing. So check it out. Calculate all the distances. You will find that now the distances are really like in the input matrix. So neighbor joining is able to convert this input faithfully in a tree. What does that mean? This input therefore, and UPGMA failed. What does that mean? This input is not ultrametric, but input is additive, right? And you can have even more nasty cases when that doesn't happen, when the metric doesn't happen anymore, that, you know, the speeds are so different that you cannot add it up anymore because you get inconsistencies between lineages. Now, I leave it to that. So there's even a more nasty possibility. And then it turns out they've done all kinds of modeling work, and it turns out that neighbor joining is reasonable even at the more nasty conditions. Yeah? UPGMA is horrible. I was completely wrong. But neighbor joining is a pretty robust method. So that's nice to know. Okay, so that's one. You can just run, right? But there is more. Computers have become faster. Distance methods overall are fast. You know, you step, you see you have a matrix that shrinks at any step. It's quick. Now we go into methods that are a lot slower. But anyway, computers have become faster, so they're more into use. So what have we got? Basically, what's the task? What would you hope to get? You have an input matrix. You get a tree that faithfully represents, as it happens here, the input matrix. So under the assumption of additivity, neighbor joining can do it, and under the assumption of ultrametricity, or under the condition of ultrametricity, UPGMA can do this. Okay? But the next one, this is distance-based. So the methods I talked to you about, single linkage, complete linkage, average linkage. So average linkage, UPGMA is sort of average linkage, sometimes called. Single linkage and complete linkage are cluster methods that are not used by phylogenists. Because, well, you can even reason about this. Would it be good to know? So, because biologists reason, because I don't know really the distance between clusters, what really happened, how did evolution really proceed, how did the species come about, we don't know, so let's average, then we're on the best. Right? That's the idea. Maybe you could say, but if you know the smallest distance, maybe it's not even such a bad idea. But anyway, these methods are not used in most phylogeny, but UPGMA is. Yeah? So that's still a method that is pretty widely used. But parsimony. Okay, Occam's razor. So you already saw this happening a moment ago in neighbor joining, where I said, you know, what is optimized? Basically, the total tree length, all the branches. That kept minimal. And that means, you know, you go to the simplest model if you don't know anything, right? So that is exactly what was found in 1340, roughly, it's a while ago, guys, by Occam. William of Occam was a monk. I think he lived in the UK and came to something that was called later on Occam's razor. And the only way I can do this, but if I told you the story, did I tell you the story of the Beethovenstraat? Did I? Beethovenstraat? Bicycle? No? Oh, okay, that's good. Then I tell you. Quickly. Okay. You're on your way to VU in the morning, right? And you're on a bike. You're a bit in a hurry and so on. So for some reason you come along the... Yeah, did I tell the story or not? No. Okay, then we stop immediately. So you see a guy standing at one side of the street. Okay, you know. Okay. You go on. At VU. And there you're just going into the restaurant. Oh, yeah, I forgot my mobile phone. And as you know, there is no life without a mobile phone. So the only option is there, forget about the lecture. You jump on your bike, go back. You pass the Beethovenstraat once again. You see that guy, that same boy, that's standing at the other side of the street. Your question is, what did the guy do in the 15 minutes or so that I saw him at one side of the street and now at the other side of the street? I give you two scenarios, and you pick your favorite one. That boy went into a bookstore, stole a book, was caught, jumped out, jumped on a bike, drove away, was chased up, jumped in a taxi, what do I know? So 15 minutes later he was just, at the other side of the street. Scenario A, exciting. Scenario B, he just was thinking a bit, he was nerdy, it was early in the morning. And he walked to the other side and he was just standing there. And you saw him there. What's your scenario, A or B? Not knowing what happened. You go for A, you like excitement, right? But what does your mind tell you? Not knowing. You probably agree with me that story A is more complicated than B. You need more stuff, you need bikes and even taxis, and what are people then driving the taxi, stuff like that. B is boring, but simple. So take the minimum set of assumptions if you don't know. That keeps your story the most conceptual and consistent. So that's a very general statement, and it works very often. Don't make things any more difficult than it needs to be. Yeah? Because you need to explain all of those assumptions. And of course, if you're allowed to just make any difficult model, then you can explain absolutely everything. What is the meaning then, right? And this even touches upon discussions about religion and so on, but I won't go there. But Occam's razor, he was a monk, by the way. He thought about religion a lot. That's how he came to it. And but that is used a lot in phylogeny. If we don't know, try and keep it simple. The simplest scenario is the one we would go for in the absence of knowing anything better. Okay? Here we go. This is distance-based, right? So this is converted to tree. Here we go into parsimony. Now, this was distance-based. Why are these methods distance-based? Maybe these numbers are a result of an alignment. It can be, so we don't look at it anymore. We only take the distance set, and then we make the tree. Yeah? So the alignment is the input for this table. Then you make it distance methods. In parsimony and also in maximum likelihood in a moment, we'll you look into the full set of sequences. Now, this is a simple example, of course, of an ungapped alignment once again, of let's say DNA sequences. And now we view each of these sites, positions in the alignment, telling a story. And the question is, do they all agree? Well, I'll tell you the story that column 1 tells you. That says, you know what? Drosophila is really very different from the others. Can you see that? T, and the others have A. So Drosophila is the different, is the way out, is the guy out. And column 2 says, I fully agree. I totally agree, you know. Even if this would have been a CCC here, it would have agreed fully, right? That's great. But now, column 3 says, such nonsense I've never heard in my life, right? It's clear that Fugu is distant from the others. See that? And, you know, these guys says, no, you know, you don't understand life. It's really Drosophila Fugu up against mouse and human, right? So all of these columns want something else. And the question is, could a tree be amenable to each of those columns? Could a tree reconcile all these different opinions, if you like, of each of those columns, right? Now look at the tree. So what do we got here? Can you understand why this is 1 and 2? Is that a distance? No. This is column 1 and 2 in the alignment, look, because this is Drosophila versus the rest. So column 1 and 2 in the alignment support this split. The notion of Drosophila against the rest. Here. Right? What is this column doing? Number 3 is setting Fugu aside, apart. Here, 3. Yeah? And these groups, 2 is here, and 6 and 7 are here. Add these values up, add these columns up, do you get related to that? You see a relationship? This is 2, this is only 1, this is 2, this is only 1. So in a perfect world, absolutely perfectly perfect world, this might happen. But I guarantee you, there won't be any alignment in your hands where this will happen, okay? It's not going to happen. This is heaven. This is heaven in Floyd. And, you know, on earth there is no heaven, as you might know. This is earth. Okay, anyway, so this is the game we want to play. And basically, what is the game? What do? We have these stories, and now we need a method. So we just absolutely generate all possible trees, right? And then we do this, and we pick the one where each of these columns agrees, where most columns agree to the tree. Brilliant idea. How practical is that? That's the problem. I told you something that generating all possible trees. I showed you that plot. Okay, anyway. They still said, well, do this anyway. So what are we going to do? Use heuristics. Anything we can cut back, you know, totally unlikely trees. We don't do, and you know what? Let's say if we get less columns, then that helps too. You don't need to calculate over each of those columns and so on. What is a column we could rule out immediately? It's a fantastic column if you want to predict functional importance of a site. What would you like to see? What about a site that is totally conserved? Fantastic in alignment. You jump up. Yeah, I found something. But here, if it's 4 times A, does that help? No discrimination. Can't do anything. So they're out. So you can write off a number of these things. And what is a simple trick? They say here, well, you know what? Let's say that we only use sites where there are at least 2 different letters, otherwise you won't get a difference. And each of those letters should happen at least 2 times. So if you do that, and you could do something else, that's a way to get rid of all the white blocks. Because what's the problem here? There are 2 letters indeed, but G is only happening once. Not good enough. So this column is fine. You have an A happening twice and a G happening twice. That's already enough. And you even have a C happening twice. Very good informative column. They call those informative columns. Just people, you know, trying to cut back corner cutting, but this is what you have. So now you have only to calculate through 3 corners, which helps you. Okay, now we do another thing. And this is already done by Dayhoff. I respect Dayhoff very much, also because in her matrix and her tree treatment, she already did this stuff. So what have we got here? This is one site in the alignment, one position. It has over the 7, how many sequences? Over the 6 sequences, has the letters G, T, A, T, A, T. And the idea is now, how would this have evolved all the way from the common ancestor? And what do you do to find, and what is the maximum parsimonious letter, meaning We want a minimum evolutionary model. So how are we going to fill in these sites? And this is a way to do that. You say, this is what we have. So what could happen here at this common ancestor? Well, easiest choice is, if you make it a G, that means you get a mutation to T. And if you would have made it a T, you get a mutation to G. So these are the two possibilities. If you make it an A, that's nice, but they have two mutations. So G or T is the best here, right? So you enumerate with this all these sites, and here you get, then that here is some T here, T possibility, so that means GT. This would also be GAT here, and GAT there. And now, so we can pick from here, 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 and here. This is fixed, of course. And what do? You first go up, enumerating it, and now you go down, trying them, finding out then, in this case, that if you pick the letter T here, T to a T, no mutation, T here, T there, that now you see here the mutations coming up, that these are your ancestral sites. Here you get a mutation, of course, from T to G. Here you go from T to A with a mutation, therefore, and here you go from T to A as well. So 3 mutations. Try any other letter, you will find that you need more than 3 mutations. So Occam's razor, the minimum solution here is fill in the T's, you only have 3 mutations. Right? Anything else might lead to some more mutations or maybe the same. Nevertheless. So you do this for each of those, and that is what you call backtracking. Go back and then forth again. That's how this algorithm is called. Dale already did it, but that is used a lot too. This man wants to come in, so speed up. So, because I want to show you the other class. So this is, at this stage, I tell you the little story I have to, I promise. So, I was in a lecture room, long ago, I can't even tell when, at least 20 years ago, probably more, 25, something like that. The inventor of, I showed it to you, I should have said, James Ferris. He was a tall American man with a big beard, with a very deep voice. But he was very unfriendly and very arrogant. Right? People didn't like him, but he was clever. And he invented this stuff for the first time. So, we're in a lecture room, big lecture room, I think 500, 600 people. Lecture theater. There was a young lady, American lady, I forgot her name now, talking about distance methods, new distance methods. This guy was of the camp parsimony. She talked for 5 minutes. He stood up and he was sitting in one of the front rows. Second row, I think. As I already told him, my paper is all complete nonsense, I can't do this, you need to, my method is the one. And she said, bloody hell, that's not very nice. I said, okay, I'll get back to this. She talked on, 2 minutes later, we did the same thing. Stopped the lady. Stop talking, you should be ashamed of yourself, Third time it happened, and then she said, which was courageous, big, important feeling guy, Mr. Ferris, I'm very sorry. If you interrupt me once again, I'll come up to you and slap you in the face. Okay, so people are all sitting, Anyway, so, he sat down. It took him this time much longer again, 5 or 6 minutes. He stood up and did it again. She walked up to the guy and whack. That silenced him. So we've seen that. I've seen one other physical interaction like that, but this was a good one, and everybody was sweating. I mean, it was what would he do? Anyway, so that's Ferris, not a nice man. He looked very much. I'm telling you the story. He looks really much like this guy, but this is not Ferris. This is Joe Felsenstein. And he was a bit bigger, had a bit deeper voice. The beard was, and he was a very kind man. He was a gentle giant, and probably more intelligent even than Ferris. So he told stories like, guys, you've been fighting. Distance and parsimony and Claydis, you all hate each other. But basically, guys, you all agree. Let me show you how you agree. There is namely something that is called maximum likelihood. Let me explain it to you. You're all on about the same. You didn't know. That's why you were fighting. Let's make peace. Maximum likelihood. So, basically he said, you know what? What is the problem? We have data and alignment or something. That's data. We want to make a tree. Let's call the tree a model. And we want the best model, the best possible tree, representing the data best. That's the idea. So what are we on about? We would like to calculate a tree that optimizes the likelihood of the data given a tree. You try a lot of trees, and you pick the one that is best in this sense. Right? That was the idea. Is that expensive? You bet. Okay, so that's the trick. And I've talked you quickly through that because there's a very gentleman standing outside, but I think I can stay here until this time. Oh, I have still 2-3 minutes. Make that 5 and we're done. You're out of here. Okay, so this is the ID, and this is just likelihood, and you've seen that. If you make this fully Bayesian, then we have this. You know, what tree would we like to say? This is the one you see in maximum likelihood. See? But in the full Bayesian framework, which you all know now you're doing Hinamarkov, you would like to find the most likely tree given the data is the probability of the data given the tree times the prior probability of the tree times the, how was this called again? Help me. Marginal. Thank you. Marginal probability. Yeah. Very good. And you could do this iteratively. So what happens now, you do this for every site, you try all trees, you combine all positions in an alignment, so you calculate yourself absolutely silly. It's even more expensive. That computers have become so fast that it can be done. But there is one technique that comes to the rescue. It's a sampling technique. It's called MCMC for the diehards, Markov chain Monte Carlo. But it's a sampling technique to make this a bit faster. Again, corner cutting to keep it sort of doable. And you know, this gives you, this is of course the posterior probability, you know, this is the prior. So it must depend, of course, also apart from the maximum likelihood, on of course these probabilities, P given the tree and P given the data. Okay, so I'll give you a feel of that. Here we have an alignment. What can you do in maximum likelihood? Here is one column in the alignment, and we are going to do all of this for each and every column. So this might be a possible tree. We have these 4 sides, and maybe they hang together like this. Another possibility would be, no, it's like this. So here we have position 1 and 2, and here we have position 1 and 3 together, and 2 and 4 together. Different trees, right? Which one is the best? Which one will, according to this data, be the best possibility? So what we are going to do, use maximum likelihood to put a handle on that. What is the best? And what are we talking about? We talk about probabilities of mutation, that this one descends into X, and X descends into A and into T, and Y descending into C and G, right? And this is all probabilities, and we try to optimize those probabilities. That's the idea. How do we do that? This was on an earlier, this is the simple model, a Jukes-Cantor model, where this is the probability given an evolutionary distance or time, right? So we're going to use this. So basically what we're going to do, I'll give you an example here, that if we want to find this tree, a tree like this, we have the probability from Z going to X, from Z going to Y, from X going to A, X going to C, and so on and so forth. We use all of these independent probabilities. That's why you may multiply them. And if you do that, you get a score. And basically, you try this for all possible trees, no matter how big they are, and you pick your best one. So you need an evolutionary model, but these probabilities can be filled in by using an exact model. Jukes-Cantor or Kimura or anything more elaborate. There are many, many models you could use. So you can strictly define how evolution goes about, and then you can be pretty sure that given that scenario, Occam's razor perhaps, or something more complicated, will give you the best tree. No. A few minutes, okay? He has arrived from 3:30. That's when the next hour starts. We're not there yet. So, maximum likelihood. So this is, okay. So you can read this, the pros and cons of maximum likelihood. This is a greedy method going by quart. So we have a big computational problem, right? And this is not a method that says, okay, let's work in groups of 4. We make small trees. We have a big set of sequences. We make trees of 4, and then we connect trees of 4 in a greedy way. You can look at that at home. One last thing I give you a feel, and then we all walk out and make this man happy. I promise you to show you these red numbers. What is that? This is how reliable is the split level. How to do this? I show you. This slide is easy. We have an alignment. This is the input alignment. We use a method, any method, UPGMA or neighbor joining. Stay with me for 1 more minute, then I can put this in your head and you can walk out. This is the tree that we get from the true alignment. Now we resample the alignment. We make it random. We do drawing with replacement. We take a column randomly out, we put it in the alignment, we put it back in the hat. So you see that sometimes you can have multiple times column 1 and 2 times 6 and so on. You do this randomly. You have a length, you keep the length of the alignment. You do this 1,000 times, randomly. You get all different alignments. You calculate your best tree given the alignment. You have now all these random trees, given each of the resultant alignments. And now you look, for example, take the split BE here. Is that respected in the random alignments, in the random trees? Yes. How about this one? Yes. How about BE here? Not respected. So if the number of samples would be 3, you say the score is 2/3. Right? Just the frequency, how many times out of 1,000 or 100, whatever you do, is a split, and you convert it to a number, so this will be roughly 70 here, 2 out of 3, and these are the numbers you see here. And that's why here, this biologist probably thought, if this number drops below 50, I don't trust it anymore. Okay? Show it then. This is exactly the same thing. What is another thing? This is all just a few methods that you can look if you want. There is a lot. All kinds of methods. Here the gentle giant again. He did one thing that I want to show you. You know a tree, half a minute, sit down, or we talk on for 10 minutes, and I lock the door. Hey guys! Okay. This is a tree, right? It doesn't go to a line, right? To a cable. So you have to flatten it. Look how you can represent the tree in a string. This tree can be put in the string. You can even add a branch length if you want. And even under this string notation, you can put each of the names that you might have here. Yeah? This is how old-fashioned people send their tree data just as one line, and you can calculate. This is called Hewitt format, which happens to be the village where Richard Felsenstein was living, the gentle giant, so he also made these things. He did a hell of a lot of stuff, this guy. He needs a Nobel Prize, I think, but I don't know. Okay, I think I did it. Yeah, this is just all wrapping up stuff, so I'm done. Go to your question.